Good morning, student. Today, in the series of my electrochemistry lecture, I will discuss the Debye-Huckel limiting law. In my previous two lectures, I had discussed the first part, I had discussed the history of Debye-Huckel theory, and in this particular lecture, I will concentrate only on Debye-Huckel limiting law. Why it is called Debye-Huckel limiting law? And as I have already discussed to you that in order to clear understanding and novelty and clarity, I have divided whole Debye-Huckel theory into three parts. I think this is part number 2. And if time permits, then I will also discuss the part number 3, that is Debye-Huckel-Onsager theory. Now, as you know that there are a large number of books are available in our library for the electrochemistry, but let me confess that, and I have also today I have brought that book also. I will show you that book, the excellent book, and there are two parts. This is part number 1, Modern Electrochemistry by Ghosh and Reddy. So I have taken some of the important information from that Ghosh and Reddy, and I also referred this very traditional book of electrochemistry, that is Samuel Glaston, for complete derivation. And in addition to that, I have also referred some part of this derivation based on Levine physical chemistry. Okay. Now, as you know that in my second lecture, I have also derived the role of chemical potential and thickness of the ionic atmosphere. And I have derived these two final form of the Debye-Huckel theory, and you are all aware of all the terms, but the most important terms here, that is the kappa, and second is the permittivity, or sometimes we call it the dielectric constant, which is very important. And you know that generally we consider that, suppose this is a central ion and it is surrounded by the opposite ions, and basically it is actually ionic cloud. I must write like that. It is an ionic cloud, consists of oppositely charged ions, and there are other things. And ultimately we have derived two equations, and you all know that most important part is that inter-ionic attractions or Coulombic attraction. That is our part, and I am getting two equations. In one equation, there is no K value, that is represent the thickness of the ionic atmosphere, and where whatever the change in potential at a distance r, there is no surrounding ions. But in second case, yes, there is a thickness of the ionic atmosphere. Generally, we can write 1 upon kappa. So, the Debye-Huckel limiting law, why it is called limiting law? Because it is based on very dilute solution of the electrolyte. And of course, there is the extended form of the Debye-Huckel limiting law. But today I will not discuss the extended form of the Debye-Huckel limiting law for appreciable concentration. I will only concentrate on the Debye-Huckel limiting law. So, the derivation is based on this equation. Of course, I will use two other equations. One is Born equation and other things. I will explain these things. Now, as you know that before I start the derivation, I must write the final equation of Debye-Huckel limiting law. Okay, then of course I will derive. Now it is very simple that this is called activity coefficient. So log of activity coefficient equal to minus 1.8 into 10 to the power 6. It is the valency, D is the dielectric constant, and T is the absolute temperature, and mu is the ionic strength. But suppose you are changing the medium, relative permittivity or the dielectric constant. So basically, we do all such type of experiment in the room temperature, and water is a universal solvent. So basically, we write, if you know the dielectric constant of water is approximately 80. So the Debye-Huckel limiting law can be expressed as log of I, and if I solve, if I put the value of dielectric constant and temperature, room temperature, so I will get a value. This is 0.059. No, I should not write the A. It is not A. So I can write like that: log of gamma, the activity coefficient, for I species is equal to minus, or you can write Q Z I species under root of mu. This is the formula. But it is for one species. But basically, our objective is that the application of the Debye-Huckel limiting law is the actual determination of mean ionic activity coefficient. I will explain gradually. So mean ionic activity coefficient means I should write like that: log of gamma plus minus, like that. And then it is a value of, I will explain that why we come 5, then z plus, z minus, then under root of mu. Okay. So now how do I explain this thing? That is the Debye-Huckel limiting law. Now, why we are dealing with the Debye-Huckel limiting law? Because with the help of Debye-Huckel limiting law, one can determine correctly the mean ionic activity coefficient. And it is in the course of the thermodynamics. I think we have already studied, so I will not go into details of that activity coefficient and activity terms. But because it is a dilute solution, sometimes the solution is dilute, because generally activity is equal to stoichiometric concentration and activity coefficient. If the solution is very dilute, so the stoichiometric concentration is exactly equal to the activity of the things. But because when there is electrolyte dissociates, there are two ions. So basically, if I want to write the mean ionic activity coefficient, so that is gamma plus minus, and in some books it is written F also. But here I am using the gamma term. So it is always remember these things. And there is a relationship between the activity and chemical potential, which is very important, because ultimately when I will derive that Debye-Huckel limiting law, so I have to think about the work done, or the electrical work, or the change in free energy. So therefore deliberately I have written, there is a very, very common equation in physical chemistry, that mu is equal to mu zero, chemical potential of the standard species, or the sometimes considered the ideal species, and RT, natural log of activity. And if I am talking about the electrolytes, or you can write AB also, you can write A plus B. There must be some specific valency and number of ions. So suppose the number of ions in some spaces, I can write nu is the number of ions and Z is the valency. And suppose there are two types of ion, so there is a possibility of positive ion, there is a possibility of negative ions, valency may be Z. So you must be very much clear about the terminology you are using. So if I am talking about this first species and this is the second species, cationic species and anionic species, because you know this is system that maybe if central ion is positive, so surrounded ions is negatively charged. I mean it is negatively, surrounded ion is positively charged. So I total chemical potential due to the positive ion and this is due to negative ions. So therefore I have deliberately written the mu 0 of standard of this cation and standard of this anion. Similarly, activity means concentration and activity coefficient. So ultimately, I am getting, that means what does it mean? That means if I understand, if I know the chemical potential, so I can very easily calculate the free energy or the work done for these things. And you always remember these things. If it is a mean ionic activity, gamma plus minus, so number of ions of positive, number of ions of negative ions, and it is again activity coefficient of positive ion, number of ions is here negatively. So in order to understand the Debye-Huckel limiting law, you have to understand the activity and activity coefficient, because relationship is, if you ask me, sir, what is Debye-Huckel limiting law? So it relates the activity, mean ionic activity coefficient of electrolyte with the valency as well as the ionic strength. And whenever we are talking about the ionic strength, there is a question of concentration and valency. So that is the thing. Now I will derive these things. Now it is an imagination. Why it is an imagination? Because suppose this is the normal cases and there are surrounded ions. Maybe, and solvent is also there. Solvent is also there. And this is the R distance. So it is a charging species like that. Suppose you imagine that you turned off all the ions and you imagine there is no ions like that. So that process is called the discharging process. Okay, so now it is completely empty. Now the second thing is that after discharging process, suppose you are bringing some ions from the infinite. So first is the discharging process and second is the charging process. So in order to bring all those ions, so we have to do some work and there is a change in free energy. So in one case, ideal situation, another case is the real situation. And the difference between the free energy of that ideal condition and the real situation, that is equal to the electrical work done. So we have to calculate that electrical work done. And then, of course, we have to substitute the value of that kappa and other things. You will get the final equation. So therefore, you see that chemical potential is the sum of following terms. Whatever the ideal condition and that is the excess condition. So change in excess is equal to change in free energy with respect to number of ions and other things. So total free energy and the ideal free energy. Ideal free energy means there is no ions like that. Now for that, how do I calculate that electrical energy or the work done? So we have to take the help of electrostatistics. Electrostatics, and the equation is called the Born equation, and it is available in the book of Bockris and Reddy. So work needed to charge an ion at its chemical potential, because what is first thing, that the Coulombic interaction of ions have been turned off. Because what is the difference between their Oswald dilution law and Arrhenius equation and this equation in Debye-Huckel theory? There are some positive ion and negative ions. So there is a electrostatic attractions, and due to this there is a deviation from ideality. But if you just speculate, I am just calling it as a speculation. It may not be possible that you turn off the thing. There is no charge, nothing. So no interaction. So this is ideal condition, empty. Now second thing, charging. That means charging the system. You are bringing the ions there. So that is actually real situation. So the difference between the ideal behavior, there is no charge, and second part is the charging. So this difference between charging and discharging, that change in free energy is equal to the electrical work done. That's all. Now how do I calculate these things? So there are two steps, because there is excess free energy can be determined from the electrostatic interaction between ions. First, calculation of the potential due to ionic cloud. So therefore deliberately I am using that first equation, Z EI divided by dr, and second case Zi divided by d, only d. So first part is that when there is an ionic cloud, again and again I am just saying ionic clouds is there. And second is that calculation of amount of the work required to remove the central ion from the ionic atmosphere. So that is the things. And very simple, we'll do some very simple integration. That you see again and again why I am just using the first part of the Debye-Huckel theory. So you can derive from that equation also. Change in potential. One is R, a particular distance. No ionic cloud is there. And second, yes, there is a ionic cloud, because actual situation is, yes, there must be some ionic cloud. So why I am talking just use of electrostatics, there is an equation, that equation is called is Born equation, which was developed in 1920, and Debye-Huckel developed 1923. So I am solving this Debye-Huckel equation with the help of Born equation. I will not go into details of the Born equation, but you can mention that yes, this equation is important for this thing. Suppose, again it is speculation, all the ions are discharged. So small charges are brought up to the ions from infinity, reduce the charge in all the ions to 0. So therefore whenever I want to calculate the work, so I have to integrate from 0 charge, you follow my point, to when there is a charging, valence is E and this. So I have to integrate from 0 to that charge. So it is a reversible increase of all the ionic charge from 0 to E. And electrical work, I am just repeating again and again, repeating same thing. The change in free energy of the real system, where there is a ionic cloud, minus ideal condition, there is no ions. So I have to calculate that work, and once we calculate the work, I have to substitute the value of K, which we have already derived our first part of the Debye-Huckel equation. So this is the simple formula, that as I told you that I am using the electrical work required to form the ionic atmosphere. So therefore I am just using this kappa value here, and D is the dielectric constant. So it is very simple, you know that X for N 0 to. So X N plus 1, you know this formula. This formula is this formula. So I just solve it. So it's very simple, you know. Kappa is a constant. Dielectric constant is a constant. So say just X N plus 1. So directly, if you don't understand the integration or Born equation, don't worry for that. You simply write the actual electrical work. Now, I must confess that when I referred various books, various research paper, I found there are different types of the derivations. And one of the derivation is that you integrate first R part, then you integrate this second part is also possible. But I think because you are all first semester student, I think this is the simplest derivation. This is the simplest derivation. So without any doubt, you can use this formula, which is called the electrical work, which is the difference between the free energy of the real system and ideal system. And the last part is very simple, but cramming power is necessary because you have to substitute the value of this kappa, and you'll get the final results. So that is important. So what I am getting, valency square, epsilon, charge, and D here I am written is the that. It is clear? Okay. Now what would be the second part? Second part, I have to substitute the value of kappa in this equation. Okay. So for your convenience, I am writing this equation because we have already derived this equation in my first part of Debye-Huckel equation, where is that kT natural log of I is equal to this. Why I have written these things? Because I have already shown you that mu is equal to mu0 plus RT natural log of activity. Don't worry about this mean ionic activity coefficient. So I am using, so this is the standard value. So that free energy and work done, the relation between free energy and the work done. So from there I have written this RT. And here actually it is Boltzmann constant. So this is K, and K is equal to actually sometimes it is R by N, This is K is Boltzmann constant. So therefore I have just written here the Boltzmann constant. And the same value, there is no problem. Just you have just this value I have written here. Nothing new. So this, okay. So natural log of I is equal to this divided by kT. This kT here. Okay. And K is equal to universal gas R by N. N is the Avogadro number. K is equal to R by N. So if I write here R divided by N. So N. So what I am getting? N Avogadro number, Zi valency, epsilon square, kappa, and 2dRT. Any doubt? Okay. Yes, now, as I told you that I have to substitute the value of kappa. So in order to just, you remember the Debye-Huckel theory, we have already derived these things. This is equal to, again here is also we can change it R by N. So kappa is equal to 4 pi epsilon square dkt summation, you all know that half Ci Zi square, and half actually here is half. In Debye-Huckel theory, I also change this thing that N is the number of moles, but suppose N is equal to, if I just replace this N, C is the ionic concentration in moles per liter, and N is Avogadro number. So that Ni can be replaced by Ci, which is the concentration. N is the Avogadro number divided by 1000. So there are two options. First, you just convert it in concentration moles per liter, and then you substitute the value in that place. Or after substituting the value of K, you can change it. It is up to you. There is no problem for that. So you need just I change these things. That means this in place of Ni, in place of Ni, I am just writing Ci N divided by 1000. So that is there. So now K value is modified, K value is 4 pi n square E square 1000 dRT Ci Zi square. And we know that the ionic strength formula is half Ci Zi square, half Ci Zi square. This is the, so what can I write? Ci Zi square is equal to 2 mu. I can write. Any doubt? Very simple. So 4 into 2, so 8 pi. It is just a substitution, no rocket mathematics is there. But you have to do continuous practice in order to solve this problem. So 8 pi n square is Avogadro number, E square 1000 dRT. This is mu, ionic strength. So now my final value of kappa is 8 pi n square epsilon square 1000 dRT. So what will be the next step? Anybody? Substitution the value of K in our Born equation final. So right, again I am just for your clarity, I have again written the same old formula. Substitute the value of kappa. Again I am just for clarity I have written, again I am writing the same thing so that you can very easily understand that if I substitute here, because already n square I can write n and n is always there, so therefore n square. You follow my point? It's a very simple thing. If you are a mathematics student, you can directly solve it, but because large number of biology students are here, so I am just using very simple derivation. And you know that if I converted the natural log into log, so I have to multiply 2 point, minus is there, don't worry for that. So you see n square from n, this is n square, epsilon square, no problem. Here I just write. Now here you see that r half and where is that? There. So that is 3 by 2 like that. And 2 pi you can write like that. This 8 can be write that 2 pi and 1000 half is already there. This RT and this RT. So 3 by 2 and Zi square is also there. Zi square and dt half and this dt. So I am getting this final formula. So this is also one form of Debye-Huckel limiting law. But again, there is some problem that R is a constant value, N is a constant Avogadro number, pi is also constant, temperature, dielectric constant. So I can, if I clarify this equation. And second problem is that, as I told you, that I am concerned about the mean ionic activity coefficient, where there are different types of ion. So therefore, I have to slightly modify that equation. I am getting the final equation, but there may be slight modification. What is that modification? Same thing. That means if I substitute the Avogadro number, now I am not substituting the dielectric constant. It may be any type of the solvent, but I am just only changing the R, N, T, or I think T you cannot change it. You just substitute the value of R and other things. So log of mean activity coefficient or activity coefficient 1.823. It is a, if you just calculate universal gas constant and other things, I am not changing the dt because it depends upon the types of the solvent and the temperature. So, but for water, 78 point or 80 approximately you can call. And temperature, room temperature, 25 degrees centigrade approximately. That means you have to substitute the value of, so you will get log of I. Now this value actually, if you use this value, here you substitute the value of 78 and 273. So if you solve it, so I am getting A, or you can write, if I minus 0.509, because there are two constants A and B. When we solve the extended, you will get. So this is the partial Debye-Huckel equation for activity coefficient. But ultimately our objective is that mean ionic activity coefficient. So I have to just slightly, will take only 2 minutes to, this is final equation, okay. But in order to get the log of plus minus, I have to just slightly modify that equation. What is that? Now, just say very carefully, this is our actually mean ionic activity coefficient value. Okay. Gamma plus minus, gamma plus, gamma minus divided by 1, V plus V. This is actually total value. Now suppose I am talking about an electrolyte. You can use any AB or MX or AB or AB, you can write that, AB. So what I am getting, plus of A and plus nu of B, negative one, like that. But what happened, when you take any electrolytes, so it is electroneutral. What does it mean of the electroneutral? Electroneutral means, suppose there are positive ion, number of ions, Z plus, it should be actually in here we can write, plus number of negative ions is equal to 0. Or even some books I have seen that nu of plus Z of plus equal to nu of minus Z of minus. So you can write like that, Z, you can write like that, Z of plus minus Z of minus is equal to nu of plus nu of minus, or same thing. So that means what, sorry, here is nu of minus and nu of plus, you can write like that. So in normal cases, in place of, if I take the log, suppose I am taking natural log of, suppose I am taking natural log of plus minus. So you know that I can write that, I can write nu plus of natural log of y plus nu of minus of natural log of y plus minus divided by nu plus plus nu negative. I can write like that. So as because the solution is electroneutral, that valency is equal to the number of ions, so that it can be replaced by the Z, it can be replaced by Z negative, it can replace by Z plus and negative. But I am using the system and I have taken this derivation, this part, this is not derivation, it is simple how you write the mean ionic activity coefficient. I am taking the books of Levine, very recent edition. Only for this part I have referred the Levine book, and I have also referred the book of Bockris and Reddy. So just the solution is electroneutral. So just a very simple derivation, very simple. Just you look very seriously that nu of positive, number of positive ion, valency of the positive ion, okay, plus negative ion, total number of negative ions, plus valency of the negative ion is equal to 0. Okay. Or what I can write? I can write nu of positive, I can write like that, nu of positive charge is equal to, you follow my point, minus nu of, can I write like that? Now suppose I multiplication both the equation, first z plus and then z minus valency, like that. So if I first multiply it by z plus, so what will happen? There is no change, but again z plus means z square. So just zoom it because this size is very small. Any doubt? Second part is minus nu negative z negative multiplied by z plus. So yes, there is a z plus, this and this. And same thing, secondly, I multiplied by the z negative. That means what I write? Nu z negative is equal to minus nu plus and z plus. I multiplied by z negative. So same thing, in place of plus, nu negative, z negative and minus z plus minus z plus and z negative. So in place of v plus z plus vz nu negative, I can write my modified form after multiplication of z square and z square. Just 5 minutes, first 5 minutes. So in place of nu positive, nu negative, I have written what I have written here, this part, multiplication of z plus, and second part, multiplication of negative side. So in place of this, I have written here, and resulting part, I have written here. So here you have seen that this part is common, z plus and z minus is common is there. So, but minus is there, so nu plus and nu negative. And because z is negative, so therefore I am getting z plus z minus, nu plus plus nu minus. That means there is a separation of these two things. So in our final equation, I can substitute this value. Now it is up to you. I have given you the reference. I have taken from Levine, I have taken from Bockris and Reddy. If you don't understand, it is very simple thing, just substitution. So you can skip it out. You can directly write that valency and the number of ions. So I am doing nothing. Or if you want to read some of our other Indian good books or Indian books, the system is slightly different like that. That is what they did in place of, as I have already told you, then substitute the value of z, substitute the value of z negative, and then, so you can write like that, z plus z negative is equal to v negative, v2. So z plus, you can write like that. So final equation is that, in place of this, our first part, nu plus log of, nu minus log of I. And now this log of I we have already determined, that is actually, you see here, z plus plus. Okay. So what I can write? Z in place of this, I can write z negative and nu positive and nu negative. So this part is nu with that part. So what I am getting, this log of plus minus, then again a first equation, if you see that, our first equation is that here, same thing equation. Just that means you have written the value of f. Generally, what you have written, log of f minus a z under root of mu. So this cancel out over this. So only thing is that z plus and z negative and under root of mu. And this is a. In my next class, I will discuss the what is the value of a, how we introduce the b and kappa. That is the extended form of extended form. I will not discuss today extended form. So now it is quite natural if I, why it is limited law. If I plot a graph between log of mean ionic activity coefficient and under root of mu, depending upon the types of electrolyte, we will get different types of things. And then there's maybe some deviation, and that is called the Debye-Huckel limiting law for the extended system. So finally, this log of mean ionic activity coefficient can easily be determined if we know the value of A, if we know the value of Z, if we know the value of valency, and under, of course, ionic strength. And you all know that ionic strength is equal to half Ci Zi square. And there are other systems also that if you change the dielectric constant, other things. And I have taken the last part that application of this Debye-Huckel limiting law. I am just using some of the research papers of this published in Cuma Nova Catalyst in 2013. That the strength you can verify in your classroom also, in your practical classes also. You can determine the mean ionic activity coefficient of any types of the electrolyte, 1,1 electrolyte, 1,2 electrolyte, 1,3 electrolyte, that means NaCl or copper sulfate or whatever it is, K2SO4 like that. Any types of the electrolyte you have to take, you know the concentration and you can calculate the K. So this is some application. Prediction of Debye-Huckel limiting law, log mean ionic activity coefficient of the different ionic strengths. So very briefly, because it's a very big chapter, very big unit, I think this is my third class. First part is that the history of the Debye-Huckel, the fundamental concept. Second part is some part of the Debye-Huckel theory, where we consider the chemical potential and the value of importance of ionic cloud or the ionic atmosphere, and of course the dielectric constant. Third part, the relationship between mean ionic activity coefficient with the ionic strength. That is the third part, which is called Debye-Huckel limiting law. Fourth part will be the extended form of the Debye-Huckel limiting law, because it is limited up to certain very dilute concentration. So if the concentration is high, appreciable concentration, so we have to calculate A and B. And the concluding part, which is entirely different, where we will consider the electrophoretic effect, relaxation effect, frictional laws and other things, then we will get the final equation, which is called Debye-Huckel-Onsager equation. Then of course, the whole electrochemistry Debye-Huckel concept will be completed. Thank you very much.